complex amplitudes because we're going to assume the source frequency is understood. We're going to assume the complex exponential is sitting there. That's the cancellation I mentioned. And when we do that, all elements can be considered as complex valued resistors. The technical word is they're an impedance. That is really, it makes our life a whole lot easier. Let's go back to our RC circuit. So we're going to talk about our RC circuit, and instead of it being out of real world values, we're going to consider it as being built out of impedances. So I want to be sure you notice something in the notation. Over here, this is a lowercase Vn of t. We're assuming that's Vn e to the j 2 pi ft. This is a lowercase v, which is going to be something which we know is going to be an uppercase v out e to the j 2 pi ft. So these are uppercase and these are lowercase. So what you do is you think about everything as being a impedance. All the resistors, capacitors, inductors are impedances. The source is a constant given by the complex amplitude of the complex exponential back here. So time is gone. There is no time variation in this circuit. And we have a V out. And now we want to figure out what the amplitude of the output is given the amplitude of the input. Well, now that everything's a resistor, we can use voltage divider. What could be simpler? You're going to use instead of resistor values, we're going to use impedance values in our voltage divider. So, voltage divider says that the output voltage is equal to the impedance of the capacitor divided by the sum of the impedances of the resistor and the capacitor. Just like we had before with resistors. Plug in what their impedances are and simplify a little bit. We now know what V out is. It is equal to the amplitude of the source times a complex number, 1 over J2 pi FRC plus 1. So, what could be simpler? And now to complete the story, we now know that this is true. We put back in the complex exponentials. We, if you will, uncancel the complex exponential that was lurking in the setup from the very beginning. And now we know that when the input is a complex exponential, the output is also a complex exponential, where V out is equal to this quantity. We have solved the circuit for the case of a complex exponential source. That's the way the impedance game works, if you will. So, when the circuit consists of sources in any number of resistors, capacitors, inductors, it doesn't really matter. You can pretend the sources are complex exponentials having some frequency f, and then you consider each element to be an impedance, a complex valued resistor. And now you can use all the tools we've already had, voltage divider, current divider, series parallel rules, to figure out how the output's complex amplitude is related to the complex amplitude of the source. Okay, so I'm going to show you the consequences of this. You may be a little concerned that, what about this pretend part? Suppose my source isn't a complex exponential, which is usually the case. You're going to have a hard time generating a complex exponential with any real-world source. Well, it turns out we're not really going down a blind alley. This is going to open the door to a whole new way of thinking about things, and we'll get that in succeeding videos.